Okay, again, people are settling in. Welcome back. So the next presentation is by Ziyuan Liu and Cassee Cain from Oak Ridge High School in Oak Ridge, Tennessee. And it's entitled Beyond Gaming, Using Kinect for Xbox 360 and Computer Vision to Analyze Human Gait.
Welcome and good morning. I am Ziyuan, and this is my partner, Cassee Cain. We're more than privileged to be here today at the Siemens Competition, representing Oak Ridge High School. The title of our project is Using Kinect for Xbox 360 and Computer Vision to Analyze Human Gait. In order to do so, our project focused on motion analysis. Well, what is motion analysis? Motion analysis is the science of using computer vision and computer science to analyze movement. It can be used as a diagnostic tool to prescribe treatment path and rehabilitation methods. It can help clinicians and researchers to quantitatively examine movement. It can also help children with cerebral palsy, patients with joint replacement, amputations, brain injuries, or almost any condition where movement is affected. As a matter of fact, one of the current applications of motion analysis is the lower leg analysis of amputee soldiers. We hope that our project can better assist the process of fitting prosthetics for people like these soldiers. Motion data can be easily obtained from Gait laboratories. However, Gait laboratories are not always accessible to everyone. They are both expensive and space-consuming.
So the goal of our project is to develop an inexpensive and accurate motion analysis system that is easily accessible to more of the population. In the initial stages of testing, we use a robotic manipulator provided by our sponsoring facilities as our testing subject. The robotic leg is connected to an external computer that can both calculate and record joint angle data. The robot offers repeatability and true data that can be used in comparison against our system. The robotic leg is programmed to mimic the motion of a human leg. The image below shows the robot simulating one complete gait cycle. In this video, the robot is seen simulating 3 complete gait cycles. The robot has completed 1 gait cycle, 2 gait cycles, and the simulation is complete.
On the analysis side, we used 3 software libraries to help us. The first was the software development kit provided by Microsoft Research, which offers 2 very important functions. The first retrieves color images from the Kinect, while the second retrieves depth information from the Kinect. The second library was the Microsoft Visual Studio C# library. And lastly, we included the EMGU Computer Vision library. Our software, written in C#, interfaces with the Kinect by extracting image frames with timestamps. It then immediately organizes the time position data and calculates angle measurements. We later incorporated the EMGU Computer Vision library to enable real-time optical flow tracking.
So why do we choose to use the Kinect? Well, along with being portable and space efficient, the Kinect is extremely inexpensive for the technology that it employs. The Kinect uses a charged couple device, red, green, blue camera in order to detect color. In order to detect depth, the Kinect uses an 830 nanometer laser emitter that scatters laser beams so that the charged couple device infrared camera can calculate depth through distortion. At such a low cost, the Kinect offers extremely reasonable quality. For example, when using the Kinect for its intended purpose of gaming, the Kinect is able to track up to 2 entire human bodies. However, the Kinect on its own cannot quantify this tracking data. Furthermore, the accuracy of the system is undetermined. We will both quantify tracking data taken from the Kinect and determine the accuracy of the system. Here is a brief overview of the steps taken in our project. We begin by testing for depth accuracy. We then move to real-time tracking using optical flow. We then record the knee angle of the robotic leg. Data is retrieved from the sensors on the robotic leg and compared to data taken from the Kinect through our software. By comparing the 2 sets of data, we find angle accuracy. We begin by testing for depth accuracy. To do this, color specificity is our chosen tracking method. This means that our program is trained to exclusively recognize a specific color. For the purposes of our project, we choose to track red. However, color specificity is not limited to tracking red. To test, we position a planar surface containing 3 red targets perpendicular to the ground. The surface is then positioned at a known distance from the Kinect lens. Depth data is retrieved from the Kinect and compared to the measured distance. Here are the results of our depth accuracy testing. It is seen that the Kinect is most accurate between 1 and 3 meters. However, Microsoft recommends that when using the Kinect for gaming purposes, the user stands within the range of 1.2 to 3.5 meters from the Kinect lens. This is because when the Kinect is being used for gaming, the Kinect aims to track the entire human body rather than specific points. It is seen that in all values in our preferred depth range, the error is under 5%, which is very reasonable for such an inexpensive system.
Step 2, we tried real-time tracking. In order to do so, we used optical flow tracking, which detects motion on a pixel-level area. Specifically, we used the Lucas-Canade algorithm. The optical flow method requires the comparison of 2 consecutive frames in order to find the motion between each frame. In order to effectively execute the Lucas-Canade method, the algorithm requires 2 things: a high frame rate or the slow motion of the tracked target. The Kinect then returns the pixel values as real XYZ in meters. As you can see, the selected points, P1, the hip, P2, the knee, P3, the ankle, are tracked immediately while their values in real-world XYZ in meters are returned. And here's an example of our tracking target.
After the 3 points of interest have been selected, our program triggers a mathematical operation that calculates an angle. Using the points defined in the previous slide, we define vector u to be the vector from the knee to the ankle and vector v to be the vector from the knee to the hip. We define the initial position of the robotic leg to be 0 degrees. The knee angle is the degrees from the initial position, or the supplement of theta.
Step 4, comparison. We compare our 2 sets of data. The first retrieved from the sensors on the robotic leg, representing true value data, while the second was retrieved from the Kinect through our software. The accuracy of the Kinect was quantified by placing the robotic leg on 3 gait motion settings: 2D fast, 2D slow, and lastly 3D fast. Now, the difference between 2D and 3D is that in 2D, the leg is limited to extension and flexion, while in 3D, the hip part of the leg is enabled to rotate. The accuracy was quantified using the root-mean square error method. This video better demonstrates our post-processing evaluation. As you can see from the video, the blue demonstrates true value taken from the sensor, while the red represents data from the Kinect through our software.
The first test we executed is 2D fast. This graph represents 2 complete gait cycles, and the root mean squared error is calculated to be 6 degrees. For this test, we used manual tracking, meaning that in post-processing, the user selects the 3 points of interest frame by frame. Positions are then returned, and the knee angle is calculated. The second test we executed is 2D slow, meaning the time needed to complete 1 gait cycle is greater. This graph again represents 2 complete gait cycles, and the root mean squared error is calculated to be 6.2 degrees. For this test, we implemented optical flow tracking, meaning the user initially selects 3 points of interest that are then tracked in real time.
For the third test, we did 3D fast. As you can see from the graph, there are 6 complete gait cycles. Now, if you would look at seconds 30 to 33, you may notice a small stall. This is actually the sensors on the robotic leg recalibrating itself. The root mean square error was around 7 degrees. This test was done in manual tracking. Because it was in 3D, it strives to mimic real human motion.
The maximum error of each test occurs at the peaks of the graph. At the peaks, the knee is at its greatest flexion, and the error is under 5 degrees, which again is very reasonable for such an inexpensive system.
We found out that using optical flow is as accurate as using manual tracking. In addition, we save up to 15 minutes in real-time tracking as opposed to post-processing. We also found out that the Kinect recorded at an average frame rate of 30 Hertz, meaning that frame rate varied due to processing power or connection speed, while the sensors on the robotic leg recorded at a constant frame rate of 200 Hertz, leading to the conclusion that there is a lack of synchronization between the Kinect and the sensors on the robotic leg. The Kinect obviously performs better when tracking slower moving targets.
In conclusion, Our program is able to control and retrieve data from the Kinect in order to dynamically determine knee angle measures. We found out that the Kinect is a viable visual sensor to use when detecting gait data. We've also discovered the Kinect is practical to use with optical flow tracking on slow-moving targets, which is acceptable because when testing on human subjects, we can control the speed of their motion.
In the future, we hope to expand our work upon human and animal subjects by analyzing an entire body or particular areas of interest. Ultimately, our work could lead to monitoring motor skill development, athletic conditioning, and physical rehabilitation. Again, we hope that our project can better assist prosthetists and clinicians in the fitting of prosthetics. We definitely believe that our system can definitely become a portable and affordable diagnostic tool, increasing accessibility on the national and international level.
Here are our references, and we would like to thank these people and institutions for helping us with our research. We would especially like to thank the Siemens Foundation, College Board, and George Washington University for allowing us to present with you today. And lastly, we would like to thank you all for joining us, and we hope you have a lovely day.